So far, we've talked about chemical reactions, and we've looked at chemical reactions in the form of actual reaction equations with coefficients and formulas. We've looked at the energy involved in a chemical reaction. We've looked at how to calculate those different values and how we come up with the change in energy for an overall reaction. Now we're going to look at a more visual, graphical representation of energy in chemical reactions. So we're going to use something called a reaction coordinate diagram. And these are simply graphs or diagrams that represent the relative energy changes during a reaction. So there are two axes on these graphs. Our y-axis is energy, and it's always an increasing energy as you move up the graph. There aren't going to be numbers with this, at least not in this class, because it's all just relative. This is just a quick sketch of what's going on during a reaction. The x-axis is the reaction progress, so you can think of this kind of as time. Again, we're not going to use actual numbers, but what we're going to use is this side of the graph is going to be the beginning of the reaction, and then as we move across, it's going to go towards the end of the reaction. So we always start on the left and we move towards the right. Now on a reaction coordinate diagram, you'll see your reactants somewhere, you'll see your products somewhere, you'll see some sort of curve in between showing what's happening to the energy. So this one would go up and then down and then up and then back down until you finally got to your products. We're going to look at much more simple versions of these reaction coordinate diagrams. The first type we're going to look at is an endothermic reaction. So again, we have our axes, energy and our reaction progress. So we're starting with our reactants and then we're going to our products. Since an endothermic reaction involves a positive change in energy, you're adding energy to the system, we're going to go up in energy as we move from the reactants to the products. So you're going to see an upwards curve, and your products will be at a higher energy than your reactants. So what do you think is going to happen with an exothermic reaction? What do you think that graph will look like? If you said it would be the opposite, you'd be correct. So in an exothermic reaction, we have a negative change in energy. Our energy is going down. It's being released from the system. So our reactants are going to have higher energy, and our products are going to be lower energy because we're going from high to low. So we're going to see a curve that goes from our reactants at high energy to our products at low energy. So those are how we can tell the difference between an endothermic and an exothermic reaction. Let's look at some other pieces of a reaction coordinate. So another term you'll see often with chemical reactions is something called activation energy. And it's exactly what it sounds like. It's the amount of energy needed to activate or start a reaction. Think about if you want to light something on fire. Fire is an overall exothermic process. It gives off energy. However, things don't just typically spontaneously catch on fire. You need to supply some energy to get it started. That supplying of the energy at the beginning is what's called the activation energy. So on a diagram, that's where you'll see a bump. This difference in energy from where your reactants start to the top of the bump, that's the amount of activation energy. In order to go from the reactants to the products, you have to supply energy to make it go up before it can go down to the products. So this bump right here shows the activation energy. And it's this distance from where the reactants are to the top of the curve. That's the amount of energy needed to get that reaction started. Let's look at how we can adjust the activation energy. If you want to change the activation energy for a reaction, you need something called a catalyst. A catalyst is a substance that lowers the activation energy, so it makes it easier to get a reaction going. But the catalyst is not actually involved in the reaction. It doesn't change anything about how the reactants change into the products. So we start with our reactants and we go to our products. So say this one has a really big activation energy. So this first curve, the solid line, is without the catalyst. If you were to add a catalyst to this reaction, it's some unknown reaction, you could lower the activation energy. So instead of being all the way up here, it's going down to where this dotted line is. That's with the catalyst. So it lowers that energy that you need to go from reactants to products. The key with a catalyst is that it is not involved in the reaction at all. It's just kind of there. The only thing that it does is change the activation energy. It's not involved at all in the actual forming of the products. So that's how we use reaction coordinate diagrams to represent energy in chemical reactions.